So the purpose of this video is to demonstrate how to calculate the average atomic mass of an element. And what I'm going to do really quickly before I go into that is actually re-explain what this is, what H1 is, what the 2 is there, and what the 3 is, why that's significant. And so a lot of naturally occurring elements, a majority of them, actually don't exist as just one. And so in this example, the number up above is actually your mass number, and the number underneath, which isn't shown here, would be the atomic number. Now hydrogen has an atomic number of 1 for each of these. So I'm going to put a 1 here, a 1 here, and a 1 here. And if you notice, remember, mass number equals your protons plus your neutrons. And so what you should remember then is that right here, since this is 1 and this is 1, that means I have no neutrons for this isotope. I have 1 neutron for this one, and I've got 2 for this one. So these are isotopes of each other because what makes them isotopes, what an isotope is an atom that has different versions of itself, and what's changing is the number, so they have a different number of neutrons. So if you notice on the periodic table, the average atomic mass, which we're about to calculate, is a decimal, and that's because we're going to find the weighted average of all of these based on their percent abundance, right? So 99% for this one, 0.8% for this one, 0.2% for this one, and then we will calculate their average atomic mass based on that. Now, obviously, it's going to be super close to 1, and if you don't get super close to 1, you did something wrong, because 99% of all of the hydrogen that is found in the world has a mass number of 1, meaning it has 1 proton and no neutrons. The other ones, this one that has 1 neutron and this one that has 2 neutrons are less common, are way less abundant. All right. So all you have to do in these problems is convert your percent into a decimal. So just remember, each time move your decimal place 2 places to the left. So 1, 2, and then multiply it by the mass number. So 0.99 times my first mass number, which is 1, plus, in this case, it's kind of funky because it's already 0.8%. Don't let that, mess you up. Still move it 2 places to the left. So 1, 2, so it's going to be 0.008 times the mass number, which is 2, plus, again, move your decimal place over 2 places, so it's going to be 1, 2, so it's going to be 0.002 times the mass number, which is going to be 3. Now, I explained to you guys that when you're adding, you're going to be using the fewest number of decimal places. Well, it's kind of funky and hard to do because you've got 2 decimal places here, but in a lot of cases, the rounding, if you're following the rules for addition, it's going to end up giving you a number that doesn't even demonstrate the whole point of this. So a lot of the time it'll just round to 1, which doesn't show you like the 1.00, the actual average atomic mass. So what I'll do on a test, I'll have done the problems beforehand and decided what I want you to round to, and I will write it right after the question like I did in the problems in your workbook. So I'm going to take 0.99 times 1, and then I'm going to add to that 0.008 times 2, plus the 0.002 times 3, and what I get is 1.012. Okay, so right now I'm rounded to the thousandths place. If I asked you to round to the hundredths place, I would ask you to write 1.01. This is the average atomic mass, and it works out really well because the answer actually makes sense. It should be super close to 1 because 99% of all of the sample has a mass number of 1, and so 1.01 makes sense. The last thing you need to remember are your units. And remember, instead of using grams, because grams would be super tiny because protons, neutrons are super small, we've created this new unit called the AMU, atomic mass unit, AMU. So depending on how I ask you to round it, either one of these would be fine. If I asked for the thousandths, this would be your answer. and if I asked for the hundredths, this would be your answer. And that's it.